These are the 5.2 part 2 notes, and we're going to be finishing up inverse functions today. So let's start with what a graph of an inverse function looks like. The graph of a function and its inverse function are symmetric with respect to the line y equals x. So if we look here and we draw the line y equals x, the idea is that if I could kind of like grab it and fold it diagonally, this line here would lie directly on top of that blue line. So that red line would lie on that blue line, and then if I were to flip it the other way diagonally, the blue would lie on top of the red. That's what it means when I'm saying it's symmetric to that y is equal to x. Also, we could kind of define that as origin symmetry. So when I'm looking at this, we've already learned that when I create a function and I create its inverse, I'm flipping its x and y spot. So here we can see with this red, I've got an x and I've got a y. And then when I turn it into blue for its inverse, the x is what its y was, and then its y is what its x was. So they're flipping their spots. And when we do that, it creates the symmetry along the line y is equal to x. So I think this is actually going to be easier if we look at this in terms of making it ourselves. So we've got a function here, and let's create a table of values for the function. The table of values for the function is going to look like this. We've got x and we've got y. So we've got -2, -1, and 2. Those are the three x values the graph is giving us. The y value when x is -2 is -1, the y value when x is -1 is 0, and the y value when x is 2 is 1. So when I create my table for my inverse function, the table for my inverse function, I just flip around my x and y's. So now I've got -1, -2, 0, -1, and 1, 2. So I have these ordered pairs. So I'm going to go ahead and graph that. I will go to -1, I'll go to x is -1, and I'll go to y is -2, and I'll graph that point. I'll go to x is 0, and I'll go to y is -1, and I'll graph that point. I'll go to x is 1, and I will go to y is +2, and I will graph that point. And then I'm going to make the shape of this graph look like the shape that I had from the shape above it. Now, when I go through, let's go ahead and make that line y equals x, and we can see that it has symmetry to that line y equals x. That might not be a perfect line y equals x, but that's pretty close. So when we actually go through and flip the points, I can easily see where the symmetry is. My advice, if you are told to graph an inverse function, don't just try to I'm not good at this. I'm not the world's best at just coming up with an image out of my head. I know that it's one of my weaknesses. That's why I created that table of values. That was just as much for your benefit as it was for my own benefit, because I can't, let's say that this table of values was gone. Let's just say that I moved it off. I can't see it right now. It's over here. And I just had this table of values, and somebody wanted me to go through and graph this entire function, and I'm just looking at it, trying to figure out how it's symmetric over the line y equals x. And I go through and I draw the line y equals x, and I'm trying to figure out where the symmetry is. My mind does not work this way. I'm not artistic like that. There's some people that have very artistic minds that can see that visually representative. I'm not that guy. I'm the guy who needs to come up with hard numbers and then place those numbers down, and then I can draw my line y equals x, and I can see if it looks like it makes sense to me. That's something I can do a lot better of. If I draw the line through it, I can see if the symmetry exists, but I can't create that symmetry with that line. So I would not suggest doing it that way. I would suggest actually going through the process of finding your points, and then once you find your points, checking to see what that symmetry is. And you can do that all the time. You can always go through, you can figure out some xy values, you can make some estimates at xy values, you can make a table of values, and then from there you can make an inverse table of values. You can flip around your x and y places. It takes a little bit more time, it's more tedious, but you know you're right. It's how I do it. It's always how I'll do it. I'll go through, I'll figure out xy values, I'll create a table of values for my inverse, and then graph my function. If I want to check it, I'll quickly sketch the line y equals x, see if it makes sense, and then go from there. All right, so graphing inverse functions, we're not normally just going to straight up graph an inverse function. That's not something that we do that often. So the fact that graphs of a one-to-one function f and its inverse function are symmetric with the line y equals x tells us more. If y is equal to f of x, then the inverse is defined by x is equal to f of y. So to find the inverse function, we can replace x and y and solve for y. So here's what we're going to do. Finding the inverse of f of x is equal to 2x plus 3. We're going to start off pretty simple here. We are going to say that y, we're going to change it from f of x notation to y equals x notation. I'm going to say that y is equal to 2x plus 3. Remember that f of x also stands for y. That's why sometimes you can write my name as, just as a reminder, this is an appropriate way to spell my name because f of x is equal to y. So that still reads Mr. Yehlen. It doesn't read Mr. f of x ln. It reads Mr. Yehlen still because f of x is equal to y. So I say y is equal to 2x. Now in order to figure out my inverse function, what I do is I say x is equal to 2y plus 3. But I don't leave it like this. This is not my inverse function. They look exactly the same. What I want to do is what I've always been doing since Algebra 1. We always define our functions as y is equal to something that's happening to the x. So I want to isolate this y. I want to get it by itself. So I will solve the equation for y, and I'll solve the equation as I've always solved equations, just like I've done since pre-algebra. I'll subtract 3 on both sides. I'll divide everything by 2. And now I've got the statement y is equal to x minus 3 over 2. Now what I'll do is I'll go in, and for my final answer, I will change this y to the inverse function of x, and then I'll say it's x minus 3 over 2. And now I've created the inverse function. That makes sense. Everything there works out. I can easily say, okay, cool. Y is equal to, or f of x is equal to 2x plus 3. The inverse of f of x is equal to x minus 3 over 2. A quick way to check this, let's just plug in a random number. I want to find f of 1. So this is 2 times 1 plus 3. So f of 1 is equal to 5. So I've got this point 1, 5. So what I'm going to do to check my work is I'm going to find the inverse of 5, and this should be equal to 1. Inverse of 5, so I've got 5 minus 3 over 2. That's equal to 2 over 2, which is equal to 1. So for the inverse function of 5, it's equal to 1, which is a 0.51. This is my x, this is my y, this is my x, this is my y. I switched my x's and y's for that point. So I just quickly plugged in a number just to see if it even makes sense. This is not like the fullest check, but it does give me a brief hint. Okay, did I find the inverse function? I can check it by just finding a random input and output, and then I can plug that output into my inverse function and see if it gives me my original input. If I do those things, then cool, I've got an inverse function. Or I'm more likely to know that I have a correct inverse function. So that's how we go about finding our inverse functions. Gets a little bit trickier when I have a rational function, especially when I have a rational function with variables in both my numerator and denominator. So here I'm going to start it off the exact same way that I already did. I'm going to say y is equal to 2x plus 1 over x minus 1. I'm going to change that f of x to y, and then I'm going to go through and I'm going to say that x is equal to 2y plus 1 over y minus 1. Cool. Now I'm going to isolate y. Isolating y in this case is quite a bit more difficult than isolating y in the previous case because I've got two y's and one's in the denominator and one's in the numerator. So I have a process for this. What I do is I multiply both sides by y minus 1 just like I normally would. These cross out, and I'm left with y minus 1 times x is equal to 2y plus 1. Difficult thing here, I have to remember to distribute this x. I get xy minus x is equal to 2y plus 1. Now that I've done this, I can try to combine like terms. I'm going to subtract 2y over this other side. And now I have xy minus 2y minus x is equal to 1. I can't combine these, they're not like terms, but what I can do is I can add x to this other side. And once I'm here, now I have xy minus 2y is equal to 1 plus x. Okay, I still can't get y by itself. These aren't like terms, I can't just combine them. But what I do see is that I've got y in two terms. I've got a greatest common factor on one side of my equation. And since I have a greatest common factor on one side of my equation, I can take this out and say that this is the same thing as y times x minus 2. Both of those were being multiplied by y, and I'm just taking it out. And now I can say that y is equal to 1 plus x over x minus 2 when I divide both sides by x minus 2. And then finally, I'll put my final answer of the inverse function of x here is going to be equal to 1 plus x over x minus 2. So that is my inverse function here. I can go ahead, I can check it real quick. Let's go ahead, let it find f of 1. F of 1 is 2 times 1 plus 1 over 1 minus 1. Domain doesn't exist there. That was a bad choice for a number. Let's choose a number that actually works. Let's find f of 2. That is not going to work for me either. No, it will work for me, sorry. F of 2, so 2 times 2 plus 1 over 2 minus 1. So this is equal to 5. So I've got f of 2 equal to 5. So I've got an xy point 2, 5. So in my inverse function now, let's find the inverse of 5. I will plug 5 into my inverse function. So I've got 1 plus 5 over 5 minus 2. This is equal to 6 over 3, which is equal to 2. So now I've got the inverse of 5 is equal to 2, which is an xy point of 5, 2. And would you look at that, I flipped my x and y's again. So I've got a pretty good indicator here that this answer that I found is in fact my inverse function. It is a little bit complicated with solving because we have to distribute that x, we have to subtract that x on both sides, we've got to get terms that don't have a y, we've got to put all of our y terms on one side, we've got to put all of our terms that don't have a y on the other side, and then we have to factor out y. It's a little bit difficult, it takes some time, but it's still procedural, we can still get there. So that's how we go about figuring out that inverse function. All right. Finding the inverse for this function here. So this function here is a little bit of a special function because it's x squared. So when I look at this, I'm going to kind of explain this graphically. When I have this function, x squared, it looks like this. So if I wanted to flip this around, I would say that my inverse function of x is just going to start off by saying x is equal to y squared. But that's obviously not okay because we don't square our y's. This means that positive 2 and negative 2 have the same thing. The graph of this inverse function would look like this. That's not good for us. We don't like that. Now let's say that I limited this to only being a domain. So what I would do is I would go through and say, all right, we're only going to look at this where x is greater than or equal to 0. Just like over here, I could look at this only where y is greater than or equal to 0. If I said that we're only doing this where y is greater than or equal to 0, then I could take away those negative sides and I could look at a very specific area. I could look where it doesn't repeat itself. So it's not failing the horizontal line test with the original function, and it's not failing the vertical line test with the inverse function. I have to go through the actual process of restricting my domain in order to be confident that I'm going to have an inverse function that works out here. So this allows me to say that I've got that inverse function. And so I'll have that restricted domain. Now what I do is I'm saying, all right, we're only going to look at this f of x where x is greater than or equal to 0. So I'll go through, I'll say that x is my original function, is y is equal to x squared. I'll flip around my x and y just like I did over there. I'll say x is equal to y squared. And then I'll say y is equal to the square root of x, and we're only going to do this where x is greater than or equal to 0. We're not going to do this, well, we would say that we're doing it for where y is greater than or equal to 0 over here. So we're only going to do this for values where y is greater than or equal to 0 for our domain. So we could say that if we're only going to look at, if we have this inverse function, the inverse function of x will be equal to the square root of x. And that's going to end up giving us the only thing. So we just have to pay attention to domain. It's still going to be the exact same. It's going to be the exact same thing going on, but we have to make sure we have a restricted domain from the beginning, that we're only looking from at x is greater than 0, because when we only look at x is greater than 0, then we're looking at this part of our graph. So I'm getting rid of that back half. It passes the vertical line test. I'm restricting this to now be a one-to-one function. It's a one-to-one function from x is greater than 0 onward. It's not a one-to-one function if I do all real numbers here. So I just have to make sure my graph is restricted and held to one spot. All right, finding the domain and range. So we already know how to find the domain, and I'm not going to go through how to find the domain on this again because we've been finding this domain forever. X cannot be equal to 1 is our domain. So I can already go through and I can say the domain for this function is all values of x where x cannot be equal to positive 1. And we stop there. Now the range is a little bit different, but we now have this trick. The domain, let me change color here to write this out. The domain of the inverse is equal to the range of the original function. We learned this in 5.2 part 1. We learned this in that last lesson. So now what I can say is I can go through and figure out, all right, well, my domain for the inverse function of x, and notice that this function is the same thing from example 2. So I'm just going to go ahead and quickly copy and paste this function. So that's our inverse function. We already found that in example 2. The domain for my inverse function of x is all values of x where x cannot be equal to positive 2. Well, since this is my domain of my inverse function, that means it becomes my range of my original function. So now I can say that my range for this function is all values of y where y cannot be equal to positive 2. And there you have it. Now I have my domain and I have my range. I can go through and say that this function will never have an x value that's equal to 1. It will never have a y value that's equal to 2, but every other x and y value will be met. It will be found. And so we use our inverse functions in order to figure out what the range is of our original function. If we go up and we look at this example up here, we can see that my original function, this is a domain of all real numbers. The domain of my inverse function is also going to be all real numbers. So therefore, my domain and range there are all real numbers. It works out, and it works for every type of function that we have. So that covers everything we need to know for inverse functions. Pay attention to those rational functions. Make sure that we're doing our distribution correctly. We're looking at how to solve it. A little bit tricky, but I know that we can get there. You guys have a homework assignment tonight. Please reach out if you have any questions or concerns, and have a great night.